All right. So yesterday we had the pleasure of taking a look at basically one single differential equation. And we took a look at this one, y double prime minus 10y prime plus 9y equals 5t. We had a set of initial conditions here as well. And we went back into our brains and sort of maybe a few weeks ago and took a look at that method of superposition that we learned on how to solve a non-homogeneous differential equation. That allowed us to find our particular solution using one method, and then sort of these steps 1, 3, and 4 were very similar to the next method, which we used as well to solve this problem. So really the big difference was this superposition method to find that non-homogeneous solution. And after we reviewed that, we took a look at the Wronskian method, right? And so that one, I think, requires a little bit more algebra, a little bit more calculus to work your way through. But at the end of the day, we were able to achieve the same answer. Again, steps 1 and 3 and 4 were very similar to above. It was just sort of this step 2 in the middle that was a little bit different from the first method. And then at the very end of class, we tried to begin using this Laplace transform. And that's really the emphasis of where we want to be. This idea of the Laplace transform and how we're going to actually solve this entire differential equation without using calculus at all. And so let's kind of review this one a little bit more in depth. And before I do that, let me just drop a link in the chat for that table so we all have that. Ooh. All right, so we're going to be referring to the table. A lot of the blue numbers you see, like the ones that say like number 3 or number 1, those are all referring to which line on the table we were using, okay? And so if we sort of think about the bigger process for our Laplace transform, the first thing we're going to do is we turn our differential equation, which involves calculus, we turn it into just like a regular algebraic equation. And we do this by applying the Laplace transform to every single term that we have. Okay, and so we've color coded it here in that first line so we can really match up like what goes where. And for our purposes, every time we see the y double prime, we're going to input what we have in the orange here, that s squared uppercase y of s minus sy of 0 minus y prime of 0. And so we're actually going to be using our initial conditions in a different way and in a different step than we've done in the past. Okay. And everywhere we see the y prime, we're going to replace that with what we have here in the green, s uppercase y of s minus y of 0. And then everywhere we see a y, we're just replacing that with capital Y of s. All right, so all three terms here, the orange, the green, the purple, those are sort of going to be repeated for us in terms of how we do this. Very similar to the series solution and how we repeated the same y prime, y double prime for every problem. We're going to see that same structure here, okay? The last thing we did is we took the right-hand side, the non-homogeneous side, and we used the table to apply, I think, row number 3 here to transform this into a Laplace situation with s's, right? So we end up with a function with s's, not with t's. We do a little bit of grouping of like terms. We input our initial values, and this is where we get our solution, okay? So at this stage, at the end of step 2, we've technically solved the problem. But the issue we run into here is that everything has s's and our initial question was asked with t's, so we have to go back into the t world, okay? And that's what this last step is really about. We're applying that inverse Laplace transform. So we're going from the right-hand column back to the left-hand column to figure out what our solution is in terms of t, okay? And at the very end of class, I said, Hey folks, here's a great opportunity to practice that all that algebra about those partial fraction decomposition. And I asked you to go ahead and find values for A, B, C, and D. All right. There are a variety of ways you can do this. You can, again, set up a system of equations. You can write a matrix, whatever you feel is most accessible for you. And if you want to practice the system, I think that is a really good place to just sort of dig into that algebra and see. But how did we do on this? Were we able to find values for A, B, C, and D? Did we get stuck anywhere? How are we feeling about that? All right, we'll throw them in the chat. Let's see what we get. They should look sort of familiar to values we've seen in the previous method. So if you saw something that we saw in some of the other methods, that's good. And if you didn't, then something went awry. Well, let's see, what did you get? Yeah, I ended up with those same values as well. Okay. Now, is there anyone here who would like us to go through that? Okay, because I think that's an important thing to sort of make sure we're all feeling good about. Is there anyone who would like to see that and walked through that process? Okay, cool. So let's just set up our system of equations here. Do I have enough room? Oh, we'll see. Okay. So if we're setting up our system of equations, what we want to think about is how we take this numerator and we're going to set it equal to the equivalent numerator here as long as the denominators are all the same, right? And so for our system, we have 5 minus s cubed plus 12s squared over s squared times s minus 9 times s minus 1 equals, and let's go ahead and build out a common denominator as we go here, okay? And so when we build out that common denominator, we're gonna have, let's see, the first one I'm gonna need to multiply by s minus 9, s minus 1. Right, and when I multiply that by a over s, now I will have a common denominator there. I'm going to go ahead and multiply the second one just by the s minus 9 and the s minus 1 because it already has an s squared. So b over s squared. Okay. All right, looks like we're going to need to shrink this down a little bit to make it all fit on one line. All right. For C, I'm going to need to multiply by s squared times s minus 1. And that'll be c over s minus 9. Plus, for D, I'm going to need to multiply by s squared over s minus 9. And that will give me a common denominator all the way across. Okay. Now, before we continue here, are there any questions about which ones I multiplied, or are we okay with this sort of like setup stage? Yeah, okay. All right, so at this stage, we can go ahead and get rid of all of that denominator, and then we can go ahead and just work with the numerator, right? And so we will have, I'm going to line these up sort of from the largest power to the smallest power. So negative s cubed plus 12s squared. I'm actually going to put a plus 0s here and then a plus 5. And the reason why I'm putting the plus 0s is to remind myself that if there are terms on the other side that have an s in them, all of those will add to give me 0 on the left-hand side. Right. So sometimes we're sort of looking for what it should be, but because it's a 0, we sort of forget that it's actually there. All right. Now, I'm going to go ahead and not multiply anything out. I'm just going to write out what it would be in terms of the factors. Okay. I think that at this point, it's a good place to kind of start and say, I'm not going to multiply out any factors. All right. Only because sometimes you're going to need to, but sometimes you won't need to. And in other words, like in this case, I don't think I can find every single letter. I can't find all four A, B, C, Ds just by picking clever numbers, but I can get pretty far by picking clever numbers, okay? And so because I can get pretty far by picking clever numbers, I'm going to do that first. I'm going to see what I can find as much as I can, and then at the end, I'm going to come back and find out what I still need to figure out, okay? And I believe in this case, we could choose numbers like s equals 0, right? S equals 1 and s equals 9. And that's going to help us find a bunch of the letters. In fact, it'll help us find 3 of them, okay? So if we let s equals 0, let's see what happens. If we let s equals 1, let's see what happens. And if we let s equals 9, let's see what happens, okay? Now keep in mind that we have to plug the number in on both sides, right? And so I'm gonna need to plug 0 in on the left-hand side as well as the right-hand side. And so if I plug 0 on the left-hand side, I'm just gonna get 5 equals, and like, let's see what goes away here. This first term is gonna go to 0. The third one and the fourth one are all gonna go to 0. So the only thing I really will have left is b times -9 times -1. In other words, I'll have b times -9 times -1. And I think I can squeeze this in here. I'll end up with b equals 5/9. All right, and that is one of the values that David put in the chat. We got b equals 5/9. Okay. All right, any questions about how we found this first value with b equals 5/9? Okay. So we're gonna do the next two. I like to work with the smaller numbers first. Where did the 5 come from? Excellent. So when I plug in 0 on this left-hand side, right? I know it's confusing because we have 5s and s's, but this number, this is actually a 5 at the end. So, right, this goes to 0, this goes to 0, this goes to 0. The only number I have left is a 5. Does that make sense? Right, so it's a very long equation, but we're literally plugging in that number to everything in this line. Everywhere we see an S, we must replace it with whatever number we're substituting, okay? And so maybe let's try it with a different number, and we're gonna end up with some different values, right? So on the left-hand side, we plug in 1. We're gonna get -1 plus 12 plus 5. So -1 plus 12 plus 5, that will end up giving us 16, right? So we plug in 1 everywhere on the left-hand side, we'll get a 16. And let's see what goes away on the right-hand side. Well, this is going to go to 0 because it has an s minus 1. This one is going to go to 0 because it has an s minus 1. So the first 2 terms are already 0. The third term is also going to go to 0 because it has the s minus 1 factor. The only one we're going to have left that we have to actually evaluate is the term with d. So it looks like this will give us, by setting s equals to 1, we're going to actually find a value for d. And in fact, it's going to be d times 1 times -8, right? So d times 1 times -8. And so we're going to get d equals -2. All right. Now the last number, it's a little bit bigger than the other two, right? Perhaps larger than I would prefer to work with in my brain, but we can always grab a calculator and see what happens. So if we plug in 9 into the left-hand side, we're going to have -9 cubed plus 12 times 9 squared plus 5. And that, my friends, should give us 248 on that left-hand side. Now, of the right-hand side, we have 4 different sort of terms here. We have this one, the second one, the third one, the fourth one. Of these 4, which one will not go to 0? Yeah, the one with the C, right? Because this one doesn't have an s-9 factor. So we're going to get c times 9 squared, which is 81, times 9 minus 1, which is 8. And I believe that gives you 648c. And so c will be 248 over 648, which when we reduce that gives us the same 31 over 81 that we saw in a previous problem or the previous method. Okay. So this allows us to get pretty far. It gives us 3 out of the 4 constants, okay? Now to find the last one, let's see, we have B, we have D, we have C. Well, we need to find A, all right? Now you can actually plug in all the other numbers that you found. So where D is, you could plug in a -2. Where C is, you could plug in a 31 over 81. Where B is, you could plug in 5/9, and then you would just have an A value that you're looking for, okay? But at the end of the day, when you crank through all of that, you should find that A is 50 over 81. Okay, so this one, that last one does take a little bit more work. But if you like the plug in the number method, all right, once you've found a bunch of these, you could plug in your B, your D, your C, and you could pick a different number for S. Like you could pick 2, 3, 4, -1, whatever you want. As long as it's not one of these other ones, you can pick whatever S value you want, plug it in on both sides, and the only thing you won't know is A. Okay. So that strategy will also work, and it is definitely labor intensive to find all of those, especially that last one. But hopefully this gives you a better idea of how we actually find the different pieces. Okay. I'm going to add an additional page in between here because technology, and I can, right? So that's the beauty of this. And what we're going to do is we're going to grab this line. I'm going to rewrite it with the coefficients that we just found, all those constants, okay? And then we'll use our table. We'll be really clear about which line in the table we're using, and then we'll be able to come up with a final answer. All right. So all right. So let's write this again, but with our values. So for A, I'm putting 50 over 81 over S, plus B is 5 over 9 over S squared, plus 31 over 81 S minus 9, minus 2 over S minus 1. Okay. So we've plugged in our 4 constants here. And now what I want you folks to tell me is for each one of these, which line are you going to use in the table? Okay, so I had dropped that link earlier in the chat for you. In case anyone came in late, let me go ahead and put that in the chat again. All right, but this is the table. Like, you can use any table you want. It's not that this is the only table, but I think it's convenient to have a common table that we're talking about. So we can say line 3, line 5, line 19. Okay, now the lines will not be the same necessarily on a different table if you choose a different one, but this is the one that we'll use to kind of center our conversation. Okay. So take a look at that table, tell me which line we need for each one of those, and then we can go ahead and finish off this problem. And then before we move on to the next section, we'll do one more like this just so we can get a good flavor for this.
Should be the first one will be 1, and then 3, and then 2 and 2.
All right. So I would agree. I think this first one is gonna be line number 1. The second line is gonna be line number 3. And then we'll have 2 exponentials here to finish us off, which should make sense because when we looked at the other solutions, right? So if I sort of scroll back up real quick, look at our solutions that we had from earlier. We had some like linear terms, but we also had some exponential terms. So it makes sense to us. It should make sense to us that line number 2 should come up at some point. Okay. Now let's see. I see in the chat that we have lines 1, 3, and 18. Let's take a look at line 18. Okay. So in line 18, I think if we had s squared, that's not squared, s squared minus 9, we could definitely use line 18. Okay. But it's like these really small pieces where it's like s minus 9 versus s squared minus 9 that make all the difference. Okay. And so in this case, we are going to be focusing more on the top 3 lines of this table. All right. And so let's finish our problem here. We're gonna, for each one of these, I'm gonna take those constants out to the front, okay? And just because this is one of the, we haven't been looking at the Laplace transform that long, I am gonna take the time to write out this line. But if you are at a point where you're like, I don't feel like I need to write out this line, that is entirely okay, all right? But if you're still trying to connect the dots, I hope that this will be a little bit more beneficial to you to help you figure out how to use that table. Okay. Oh. Okay. So all I've done is just say, here are the 4 inverse Laplace transforms I want to find. And I'm even going to write my s squared as s to the 1 plus 1. And the reason I would do that is that actually tells me what my n value is, right, for that second one. I think the other ones in our answer are a little bit more straightforward. So it's less important that we figure out like what a value is, because I think the last 2, we can tell what our a value is right away. But it also wouldn't be a bad idea to write here like a is 9, a is 1, right? Like all of those little things, those are for you. They're not for your instructor, right? They're for you to make sure you're plugging in the right number so that you can get the right answer that you want to get. And so as we finish off this problem, we end up with 50 over 81, let's see, times 1, right? The inverse Laplace of 1 over s is 1, plus 5/9 times, let's see, this is line 3, t to the first power, right? Because n is 1, plus 31 over 81. Let's see, this is the line 2, so e to the 9t. And then the last one is minus 2e to the t because a is 1. All right. And so it would make perfect sense if you just wrote out your answer like this without all those extra ones in there that you know are actually ones, but I just wrote out so we would make sure we knew they were ones, right? But this, I mean, except for the order, right? The order of the numbers or the order of the terms is different than what we found in the other two solutions. But if we were to just make sure we're really clear about this, these last two, those correspond to our y sub c, and these first two correspond to the y sub p that we found in the other methods, okay? And so, whoops, let me sort of zoom out a little bit for the second half of this question, right? Like what we focused on today. We didn't do any calculus. And that's sort of a weird thing to think about, right? We see these differential equations and we're like, well, of course we have to use calculus. But the neat thing is there's actually a lot of ways that you can sort of, it's almost like when you first learned about U substitution, and with U substitution, you had like this really complicated situation. You turned it into something more simple, like you were almost looking at it in a different world, the U world. And then at the end of the problem, you put your X's back in, right? We're kind of doing the same thing here where we're saying, let's move into algebra land, right? That's step one. Step one is turn calculus into algebra. Once we've turned the calculus into algebra, we get a solution, right? We get a solution in step two, but then we have to turn it back into the land where it came from, the one with the T's in it, okay? All right, so I think it would be beneficial to try one more. We're going to do a first order differential equation, okay? And I do want to let you know, in case you have not looked at this week's homework yet, there are 2 extra credit problems there. So if extra credit is something that you were looking for, there are 2 problems that are each worth 5 points. And they are third order differential equations. So I know the third order is not something that we've done in class, but I think it is a nice extension of what we've done here. And so if you feel like challenging yourself a little bit, if that's a place that you find to be a useful challenge, then that option is there for you, okay? All right, so let's take a look at example 10. We haven't seen a first order one in a while, but I bet that you could find a different method to solve this problem, okay? And the method that we're going to use right now is the Laplace transform. All right. Okay, so if we think about our question, we have right here a situation where everything is sort of in calculus land. And by calculus land, I mean there's like a y prime, right? That is a derivative. And so we're going to change everything into algebra land. All right, so we're going to go from calculus to algebra. And so we're going to take the Laplace of every single term. And in this case, we have 3 of them. So we're going to take the Laplace transform of y prime plus 3 times the Laplace transform of y, which is going to equal, I'm just going to go ahead and keep this 13 out as a constant, equals 13 times the Laplace transform of sine 2t. Okay. Now the y prime and the y, those are going to be exactly the same as what we had in the previous problem. Okay, and so those won't change. But on the right-hand side, we are going to have to use our table. Okay, so on the left-hand side, we should get, see, I think we did green for the y prime and purple for the y, I hope. And the Laplace transform of y prime is s uppercase y of s minus y of 0, right? And so that's something that we defined yesterday. Plus 3 times uppercase y of s. And that was something else that we defined yesterday. Okay. And which line in the table should we use to help us unpack that right-hand side?
Seven.
Yeah, we're going to need line 7. And I noticed that it says sine of AT. Let's be a little bit more specific. We're going to use line 7. And what is our A value?
2.
2. Good. So we're going to use line number 7 with A equals 2. Okay. All right. So that means we're going to get 13 times A, which is 2, over s squared plus 2 squared, right? So that's if I just plug it in, but we know we can clean that up and say 26 over s squared plus 4. Okay. All right. So we've taken our question and we've turned it from calculus into algebra. All right. Now for step 2, which I think is really almost like the second half of step 1. But for step 2, when we go ahead and plug in our initial conditions, we're going to plug in initial conditions and isolate uppercase y of s. That's going to give us our solution. Like at the end of this step, we have a solution. It's just in the wrong world and we have to translate it back. Okay. So I'm going to go ahead and plug in my initial conditions here. And everywhere I see a y of 0, I'm going to go ahead and replace it with a 6. Okay. And I'm going to sort of collect my terms, the ones that have the uppercase y of s. I'm going to go ahead and bring those to the front. All right. So I have uppercase y of s. And if I factor that out of these two, I'm going to have s plus 3. Yeah. And then minus, instead of y of 0, I'm going to put in a 6. And all of that equals 26 over s squared plus 4. Right. So I've substituted things in. Now I just need to isolate my uppercase y of s. And so I'm going to do that by going ahead and adding 6 to both sides, and then I'm going to divide by s plus 3. And so that will give me uppercase y of s equals, let's see, 26 over s plus 3 times s squared plus 4 plus 6 over s plus 3. So let me just pause here for a moment. I did sort of skip a couple steps, right? Are we okay with how we ended up with these two fractions on the right-hand side? All right. Now I'm going to do a little bit more work here, knowing that I'm headed into an inverse Laplace transform. And so if I can have a single fraction rather than multiple fractions, my life will be a little bit easier. Okay, so I'm going to go ahead and make a common denominator, which means that I'm going to multiply the second fraction by s squared plus 4 over s squared plus 4. That's going to give me 26 plus, let's see, 6s plus 6x squared plus 24 all over s plus 3 times s squared plus 4. And I'm going to clean that up just a little bit more. And I'm going to get 6s squared plus 50 over s plus 3 times s squared plus 4. Okay. Now you can kind of do this step in step 3 if you want, right? Like you don't have to clean it up here, but I sort of like going into the inverse part, knowing that I've sort of made it as straightforward as I can. Good question. So over here, this came from 6 times s squared plus 4. Yeah, so when we distribute, we'll end up with that 6s squared plus 6 times 4, which gives us 24. Cool. Okay. All right, so now we are ready to read our table backwards, right? And we are going to apply the inverse Laplace of y of s, y of s, which will give us our solution in T-land. Okay. So we're going to have the inverse Laplace of y of s. All right, so that's my inverse Laplace of the left-hand side. Now I'm going to say also find the inverse Laplace of the right-hand side. I feel like you folks are getting my end of summer handwriting. I'm really sorry. All right, well, we have an s plus 3 and s squared plus 4 on the bottom there. All right, so we're looking at this. I hope our first instinct is, well, we're going to need partial fraction decomposition, right? And I hope it's sort of celebratory, like, yay, this is a technique that I know. It might not be, and that's okay too, but we are going to use partial fraction decomposition here so that we can have like an a over s plus 3 and something else over the other one, right? So I have an s plus 3, I have an s squared plus 4. I know I need a constant on top of that first one, right? I know I need a constant because on the bottom I have a linear factor. What should I have in the numerator of the other fraction? Good, good. Yeah, we're going to need a linear term up there, right? Yeah, I know what you mean. I feel like the X and the S are so suspiciously close on the keyboard as well that I keep finding myself typing X. So if there are any typos in the homework, it should all be S's mostly. All right, so just so you know. But yeah, we want a linear term on top here, right? What if I had, let's play a little what if for a moment. What if instead of s squared plus 4, let's find a good space for this. What if I had s plus 4 squared? What would I need in the numerator? Exactly, exactly. So if I had s plus 4, that quantity squared, I would only need a linear term on the top because that denominator is a factorable quadratic. It is reducible, right? It's only in our irreducible case, then we put 1 degree less, okay? All right, so now that we've got our setup good for our partial fraction decomposition, let's go ahead and see what we can do. So we have 6s squared plus 50, my goodness, over s plus 3 times s squared plus 4 equals, let's see, I'm going to need to multiply the first one by s squared plus 4 over s squared plus 4. I'm always so paranoid I'm going to forget to distribute something that I will pretty much always put those parentheses there just to prevent myself from making that mistake. I'm sure if you look back on my years of academic work that I was graded on, there are some silly mistakes along the way that I just make me so sad. So this is a result of years of getting things wrong, and it is something I would prefer that you don't have to experience, right? If all it takes is a few parentheses to make it a little bit better, why not just put them in there? All right, looks like we've got our common denominator, so goodbye to the denominator, and let's focus on that numerator. 6s squared plus 50 equals a times s squared plus 4 plus, let's see, bs plus c times s plus 3. Right. Now again, I'm going to see how far I can get just by picking clever numbers. And it might not be that far, but if I can at least find something, that's better than nothing, okay? So a good number to choose here would be, you tell me, what's a good number to choose here? Yeah, let's pick a -3, okay? And just to be really explicit about this, -3, if we plug that in for s, will make one of the factors go to 0. That means this whole clump is going to go to 0 when I plug in -3, right? So it's not just that we're picking random numbers, we're seeing how can we make some of the things 0 out. And so we'll get 6 times 9 plus 50 equals a times 9 plus 4 plus 0, if you wish, okay? I believe the left-hand side, let's see, 6 times 9 is 54. So we get 104 equals 9 plus 4 is 13a. And I think this actually divides out nicely to give us a equals 8. All right, but if I could get a confirmation on that, I don't always trust my arithmetic these days. All right, thank you. All right. Now, for some of you who've said like, oh gosh, she talks a lot about system of equations, but she never really shows the work. Let me just take a moment and actually show what I would do like every single step from here, okay? So here's the deal. -3 is the only real number that I can choose to make one of the factors 0 out, because there's no number I can plug in, no real number I can plug in for s in the s squared plus 4 to make that term 0 out, okay? So I'm almost forced to set up a system of equations here. And so when we set up a system of equations, part of the reason that I've been avoiding that is because I don't really like foiling things out that much, right? Like multiplying out all the polynomials. But that we are going to do that if we want to set up a system. So this first one's not so bad. I'm going to get as squared plus 4a, right? All I'm doing is distributing that a. So as squared plus 4a. And then over here, I do need to multiply my, my binomials. So I'll get plus bs squared plus 3bs plus cs plus 3c. Okay, now that's just a step you want to probably run through your head one more time and make sure that you have multiplied things out correctly, right? Did we miss any signs here, or are we okay? I think we're okay. But when I say set up a system of equations, maybe again, I'll sort of go back in here. I'm going to bump this out a little bit. The reason I'm going to bump this out, I'm going to put a plus 0s here. Okay. And so if we think back to our, you know, younger days, maybe when we were a little bit more carefree with our mathematics, it was still actually fun. You would say, all right, let me collect all the terms that have the s squared, right? Those are all going to be like terms. And then if we had a different color, we'd be like, okay, now I'm going to collect all the terms that have an s in them. Those are going to be like terms. And then we'd say, oh, maybe there's like one more set of like terms, right? The ones that don't have an s. And each of those colors is going to give us a different equation, right? And so we're going to get, if I collect all the orange ones, I'll get 6 equals a plus b. If I collect all the green ones, I will get 0 equals 3b plus c. And if I collect all the blue ones, I'll get 50 equals 4a plus 3c. Okay. So if you've been wondering how that happens, I hope this makes a little bit more sense to you, that we've got our blue equations here, we've got our green equations here, we've got our orange equations here. And you can move through this any way you want to, right? Like there's a lot of options here. So for example, one option might be, I know my A, if I plug in A here, I'm going to find my B. Another option might be, I know my A, so I'm going to plug it into the blue equation and I'm going to find C first. That's also fine. Okay. But what would probably not be a great idea is to say, I have A and I'm going to use the green equation, right? That just logically doesn't follow because it doesn't give us anything. We just still have that green equation, right? So I'm going to put the 8 into the orange equation. I'll get 6 equals 8 plus b, and we get b equals -2. And that wasn't too bad. And I'm going to go ahead and take my b value, and I'm going to plug it into the green equation. Now, I will say this, if you feel like you are someone who tends to make small mistakes, right? If you use your A to find your B, and then you use your B to find your C, well, if your B is wrong, your C is going to be wrong, right? So you're almost getting 2 answers wrong because one was wrong. You can sort of avoid that by saying, I have my A, I used it to find this one, but I also have my A and I can use it to find the other letter. Like that's also fine. But I think we're good with our B value here. So let's plug it into the equation with the smaller numbers. All right. And so we're going to get 0 equals 3 times -2 is -6 plus C. And we're going to get C equals 6. Okay. All right, my friends. All of this work is to say we found our letters A, B, and C. Now we're going to plug those back into the Laplace, the inverse Laplace, and let's see what we find from there. Okay, so where are we at? Bottom of the page. Let's go down here. All right, so we have our inverse Laplace of A over, what did we have? S minus 3. plus negative 2s, because that's bs plus c, which is 6, all over s squared plus, I know it's plus 4, but I'm going to write it as 2 squared. Okay, I'm going to write it as 2 squared. Now, let's take a look at the different lines in the table, okay? I think we should all be fairly convinced that this first term, 8 over s minus 3, is going to correspond to line number 2. Okay. What about this second term? What about that second fraction? And if you're still looking at that table, you might be like, I don't see it, right? I don't see what we need. I don't know what line that's from. And sometimes it comes down to, well, maybe we just need to split that fraction, okay? And so I'm going to write an extra line in here for us. I'm going to have 8, the inverse Laplace of 1 over s minus 3, right? That's that first part. And then we're going to have, let's see, what's the best way to do this? I'm going to go ahead and do 2 things at one time, okay? I'm going to split my fraction into one fraction like this. And then the second fraction will be 6 over that denominator, okay? So I'm going to do that, but I'm also going to bring the constant out to the front. So negative 2, the inverse Laplace of s over s squared plus 2 squared. And then plus 6, the inverse Laplace of 1 over s squared plus 2 squared. Okay. Now, we know for sure this first one comes from line number 2. Where do the other 2 come from? What line do we need to find for that?
You need line number 8 and
Yeah, I would agree the second one is line number 8. Yeah, and then line number 7, right? Yeah, this will be line number 7, except what do we want that numerator to be? Because we don't want it to be 1. Yeah, we want this to be 2. Okay, so I'm just annotating here because I want us to remember sometimes we have to modify things, right? Which when we learned this 2 days ago and the only thing we had to do was like modify things, it wasn't that bad. But now that it's like another step in this giant problem, we really want to make sure we have those skills fresh for ourselves, right? Okay, so using our table, we're going to get 8 times e to the 3t minus 2 cosine of 2t. And then there's a number of ways that you can turn this 1 into a 2, right? One way is you could have been more clever about what constant you're going to bring out to the front. And you could have said, I'm going to bring a 3 out, but I'm going to keep the inside at 2, right? Because 3 times 2 is still 6. You're just choosing how much of that constant you want to bring out. That I think would be very clever. I'm not always that clever in the moment. So I might just go ahead and bring the 6 all the way out to the front. And then what I would do is multiply by like that 2/2 that we had. So the top 2 would stay in, but the bottom 2 I would pull out to do 6 divided by 2. Okay, but either way, we end up with a coefficient now of plus 3 sine 2t. Okay, and so this, my friends, is our solution. Right? This might be a little hard to get on one page. It might be too small, but we have here most of the solution on one page. Okay, so that the flow of this is really what I want us to focus on, right? We're going to take something that is calculus based. We're going to transform it into algebra world. We're going to use all of our algebra skills, and primarily we're going to use partial fraction decomposition, right? But we're also using systems, and we're using matrices, and we're doing clever ways of multiplying by 1 to make things work, right? So many of these algebra tricks. And then at the end, we're able to get a solution for a differential equation without using calculus at all. All right, so in addition to the other extra credit that you have, I'd like to offer one more opportunity here for extra credit. I'll write this in the pink. We did this using Laplace transform, right? I'd like you to solve using a different method. Okay, so I'd like you to solve this using a different method. You can go back in your notes, think about what are all the ways that we've seen on how to solve something that is a non-homogeneous differential equation. This one is a first order, so that sort of revisits the earlier parts in our summer session. So maybe somewhere along the lines of like weeks 1 and 2. Okay. And so we're going to, if you want to, you have the opportunity to solve using a different method. I'm going to ask that you email this to me, or you can shoot it over on Discord. That's fine as well. So send me this being solved using a different method. Let's see, today is Thursday. Let's say by your Saturday homework deadline. Okay, so by Saturday, oh my goodness, 11:59. Okay, so solve it using a different method. If you have more than one method, you want to solve this using more than one method, you are absolutely welcome to do that as well. Okay, so much of differential equations is about just being familiar with the different methods and saying, this is the best method for this case because it is the most efficient, whereas that one might be better for a different type of problem. Okay, so use this as a chance to kind of review all the different pieces that we've looked at throughout the semester. All right, so let me take a look real quick. Where is your homework? All right, so I think instead of starting 7.3 today, because I think it's a good sort of 2-day story, which might be a really good time for a Monday, Tuesday situation. I'd like you to take a look at the homework right now. So you can access that on Canvas. Well, you know where to find it, but you can access that on Canvas, or there's the LaTeX file as well. I think the first 5 should be fairly straightforward. 6 through 9 ask you to use the Laplace transform, so sort of what we focused on today, to solve those initial value problems. Is there one that you would like for us to do together? You know, just to at least get started on that process today so you feel more confident going into the homework that's due on Saturday. So go ahead and find that file. I think 6 and 7 are first order ones, whereas 8 and 9 are second order ones. Okay, we've got to vote for number 9. That one looks fun. Okay, let's see how much fun and joy we can bring to a Thursday morning. Okay. All right, well, let's give that a go and see. All right, so this is homework. Homework number 7 and question number, nope, you said 9. Okay, so y double prime plus y equals root 2 sine of root 2t. We have 2 initial conditions, which makes sense because we have a second order. All right, so to be fair, I have not done this question yet. I mean, I did like earlier, but this summer, but not recently. So let's walk through this together. All right. So I like to lay out my work by like the chunk. So I kind of talk myself through it, right? I'm going to take a look at this. All of this is in calculus land right now. So I need to change everything to algebra land. And then I'm actually going to solve it in algebra land. Like I'm going to find that uppercase y of s. And then once I get that, then I read my table backwards to figure out my actual solution in the land I was asked the question in. Okay. And so we're going to go ahead and take that journey from calculus land into algebra land. And what do we put in for y double prime? Let's start there. What do we put in for y double prime? What do we put in for y? And let's make those substitutions. All right, so it's okay to go back into your notes and look this up, but go ahead and drop those in the chat for me. Good. Yep, that's what we want for the y double prime. And so we're going to get s squared uppercase y of s minus s lowercase y of 0 minus y prime of 0. All right, so let's color this orange because that corresponds to my y double prime. All right, plus, yep, Mark's got it. We have uppercase y of s for the purple part. Oops. And then we have to find the Laplace transform of, and I bet we can pull that constant out to the front, right? Square root of 2 times the Laplace transform of sine root 2t, right? So what line in the table do we need to transform the right-hand side? Yeah, we're going to need line number 7. So we'll need line number 7. And if we wanted to be super specific, we could say that our a equals square root of 2, right? So the more breadcrumbs we can lay out for ourselves, maybe the easier it is to be accurate in our work. All right, so root 2 times, let's see, this is sine. So I need the a on the top, root 2 over s squared plus a squared. I'm actually going to write this as negative, oh my God, negative square root of 2 squared. Okay. We can certainly clean that up a lot and we'll end up with 2 over s squared plus 2. Okay, so we have to transform everything, which means this right-hand side also gets transformed, right? All right, so we've transformed everything. Now our goal is to go ahead and apply our initial conditions and then solve or isolate for our y of s, our uppercase y of s, right? So we want to apply initial conditions and isolate our solution in algebra land. All right, so I'm going to group my uppercase y of s's together. And if I factor that out, what's left inside my brackets or parentheses? Good, yeah, because we have an s squared uppercase y of s plus a 1 y of s, right? So once we factor that out, we get s squared plus 1. Then minus s times, instead of y of 0, I'm going to do times 6. Minus, instead of y prime of 0, I'm going to go ahead and put in a 0. Right? So equals 2 over s squared plus 2. All right, the 0 is going to go away. So all I need to do is add 6s to the right-hand side. And then I'm going to divide through by s squared plus 1. So y of s, let's keep this s squared plus 1 here, is 2 over s squared plus 2 plus 6s over 1. Now I'm going to divide through. I get uppercase y of s equals 2 over s squared plus 1, s squared plus 2 plus 6s over s squared plus 1. Now this would be all fine and good, right? There's nothing wrong. If this were the end of the road, yeah, leave it like that. But we still need to turn everything back into T land. And so it might behoove us to go ahead and combine this into a single fraction right now, right? And so in particular, we could have 2 plus 6s times s squared plus 2 over my common denominator. And if we expand this out, we'll get 6s cubed plus 12s plus 2 over, oops, s squared plus 1, s squared plus 2. Right. Now we get to return to our T land, right? And when we take this inverse Laplace, we are taking the inverse of the left-hand side and we're taking the inverse of the right-hand side. Right? And so we have this inverse of both sides. We know that the left-hand side is going to be y of t, right? That automatically gives us our solution. So all we need to do at this point is a bunch of partial fraction decomposition to make this into something that we can read from the table. Oh, no. All right, how many fractions am I going to have for my partial fraction decomposition? Yeah, we're going to have two, right? We'll have one with the s squared plus 1. We'll have one with the s squared plus 2. All right, what are our numerators going to be? I agree. We need a linear factor on the top up here. Good. And we're going to need a linear factor on the top over here. Right. And so this is where I can see someone setting things up. You even got the denominators, but instead of the linear factors, you just have an A and a B on the top. Right. That's going to lead you to a very different answer than someone else who might have the correct setup here. And so this is a step where it is worth double checking and just making sure, like, is that denominator an irreducible quadratic? Then I get a linear. Or is the bottom a linear factor? Then I get a constant on the top. Okay. All right, so let's do some algebra. Let's see how far we get. 6s cubed plus 0s squared plus 12s plus 2 over s squared plus 1 times s squared plus 2 equals, all right, this is a good time to write parentheses. S squared plus 2 is what I need to multiply the first fraction by. My goodness. Plus the second one, I'm going to need to multiply by s squared plus 1. Common denominators all the way across, we can get rid of those. Now we get to focus on our numerator. Now, let me ask you folks a question. If we focus on the numerators here, are there clever numbers that we can choose to zero out some of these factors? And if so, what would you choose? Yeah, we have s squared plus 2. There's no real solution for that. And then we have s squared plus 1, and there's no real solution for that, right? So when we have this irreducible quadratic factor, our hand is forced to actually do a system or a matrix, okay? And so for that reason, I'm going to go ahead and FOIL these out as I write them in the next line, okay? So I'm going to get a(s) cubed plus 2as plus bs squared plus 2b. Let me just pause for a moment. I want you to double check my work. I know these are all positive signs, but let's just make sure I didn't miss any powers here. All right, so A, there's 3 s's plus 2as plus bs squared plus 2b. Okay. So now we do the same thing with the other fraction. We're going to get CS cubed plus CS plus DS squared plus D. Right. And again, if this were me and this was an exam or homework, I would go over this again. I would make sure that that part is correct. But I think I see C with 3 S's and then C with 1 S and then a D with 2 S's and then just a D. Because we couldn't cleverly choose any numbers, this is actually a really good exercise in let's write all of the equations that come out of this. Cubed, cubed, cubed. So I can write that as 6 equals A plus C. That's one equation. 0s squared, bs squared, ds squared. That's another equation. 0 equals b plus d. All right. 12s equals 2a plus c. That's my blue equation. Well, not that blue. And then this final two, 2b and d. So 2 equals 2b plus d. All right. We actually have sort of these two that both have A and C. And then we have another two that have B and D, right? So I think this is actually a good place to kind of leave you to finish this, all right? But if you've been curious about like how we get the system of equations, I think this is a far better example than the other ones because there's no shortcuts. We're sort of forced to go about this the longer way. You could put this into a matrix if you've had linear algebra recently and that feels more comfortable. But I think this is also not too bad to solve by hand. All right. But once you put all of that back in there, and by back in there, I mean back in here, then you're ready to sort of go to the table and figure out where these functions came from, right? And we might need to modify some things. We might need to divide by some numbers. We might need to multiply by a fancy way of saying 1. But at this point, we should be in the home stretch for question number 9, okay? And so we're going to stop our recording there for today.